do this. If I can make it. We got this. All right, so we're talking about recursion today. Oh, you know what? I got to do big cursor. It's driving me nuts. I'm going to have to search it up, but I went through the last lecture with small cursor. I got to do big cursor. I'm going to do a bunch of pointing. A lot of pointing today. Long pulling. Recursion. There we go. Okay. So we want to talk about recursion today. Any questions before we get into it? Anybody has questions, I'll be checking chat, as always. Recursion, but first let's talk about compilation versus interpretation. And I didn't have my remote on. There we go. Interpretation versus compilation. I only got a few slides on this. It's not something I want to dwell on too much, but now that you've had your hands on Java, that you've been using it for a little bit, you can start seeing the difference between these two things. So I just want to kind of point out what's going on between Python and Java. Like I said, JavaScript. If I said JavaScript, I meant Java. But what's going on? What's the difference between these two? So interpretation and compilation. Interpretation means your code is executed one statement at a time. When you run a Python script, the Python interpreter will start at the top of your file at line 1 and go line 1, line 2, and just execute all of your code one line at a time, piece by piece. And if, say, like line 1, you're defining a function, it'll store that function definition, and then when it's called, it'll go back to that definition that it stored, call that function. But it's one line at a time, one token at a time, just goes through your code and runs the thing. So when you run a Python program, runs your code top to bottom. That's it. Compilation is different. Compilation, Java is compiled, is the big difference. Python is interpreted. Compilation means before your code is executed at all, before a single line of code is executed, your entire program is checked and translated into another language. And then that other language, that code is interpreted. So the first step of compilation is compiling your code, which is translating it into another language. And this means that you need to have, that you can't have, let me rephrase this one, that you can't have any errors in your code anywhere. And one of the things compilers are checking for are type errors. So for example, if you have the examples repo, which has lots of code as the code examples for the entire semester, and you want to run the code from week 3, one of today's examples, but you went around to week 14, you wanted to mess with that code, and you made a change and broke some code, so that code's completely busted. And then you go back to week 3 to try to run that example. It won't run because the compilation process has taken the entire project and compiling it. If there's an error anywhere in the project, it won't compile. So you can't have any errors, not necessarily bugs, but errors in your whole program, like type mismatch errors and syntax errors, missing semicolons, things like that. You can't have any of those in your whole project, which is generally a good thing. It might sound bad at the surface, but it's definitely a good thing. Over your career, you will learn to love compilation over interpretation. Maybe that's a strong statement. I have, for sure. Interpreted languages are tougher to work with. With interpreted languages, you'll usually have runtime errors. So when your Python code is being ran line by line, you'll get to a line that has an error. The program will run up until that point and then crash when it hits your error. It won't give you any heads up. It'll just say, oh, I can't run this next line. I ran lines 1 through 21, but line 22 couldn't handle that one because your code's crap, and it'll break and crash. Even if that line is completely trash, it will try to run your code until it gets to that. Where this gets really scary and where I've had really frustrating bugs is when you have an error in a conditional. So like if, and then a code block that has perfectly good code, and then else, and then broken code in your else. Because you can test your program, you can run your program, everything runs fine as long as the condition is true, but then when the condition is false, your program crashes. So I tested my program. I did terrible testing. I know I shouldn't have. I should have done better testing. But I did terrible testing. I only tested when the condition was true, put my code out there. As soon as somebody uses my code and the condition is false, the program crashes. It didn't just not do what it's supposed to do. The program crashes Compilation, you won't be able to make mistakes like that. With compilation, all those errors are checked before your program can ever run. You can't run your program with errors like that. The type of, I'm going to say the type of errors that crash your program, but programs will still crash if you do certain kinds of things. But like divide by zero, that won't be caught by the compiler, but it will crash your program. But a lot of these things are checked. The types, the syntax, that's all checked by the compiler as it's translating, because if it hits any errors like that, it won't be able to finish the translation into the other language. And if that translation can't work, if the compiler says, man, I don't know what you mean, it's just going to give you an error message. Compilers are pretty good these days. They'll give you pretty good error messages to say, hey, on this line I was expecting a semicolon, there was no semicolon, maybe add a semicolon. It's pretty good about explaining that. It even gives you blue links. You just click on the link and it takes you exactly to where the error occurred, and you fix your error. So they're actually pretty good about it. But they do give us a heads up. The reason this is nice is that we're never running our code with these kinds of errors in them, with these syntax errors. The compiler is going to say, hey, maybe fix your code before you release this to your users. The Python interpreter doesn't do any checks like that. The Python interpreter is going to say, well, I'll try to run your code. I'll do my best. So that's interpretation versus compilation. And Java compiles to Java bytecode. So Java code is never actually executed. It never, ever runs. It's going to be compiled to Java bytecode, and then the Java bytecode is interpreted by the JVM, or Java Virtual Machine. And this is whenever you see these pop-ups, Java needs to update, that we get bombarded with. That's the JVM, the Java Virtual Machine, which runs Java bytecode. And that's what's actually being executed when we run our programs after compilation. All right, and that's all I have to say about compilation versus interpretation. The biggest symptom that you see of this is when you click go on your Python script, it goes. Like, it just goes. When you click go on your Java program, there's a progress bar that goes along the bottom of IntelliJ, and you sit there and you wait, hopefully just a few seconds, but sometimes like up to a minute or so. For very large projects, it could take minutes. That's the compilation process running, and then finally your code runs. But if you click the go button again right after that, it doesn't have to recompile everything. It will go immediately on the second time if you didn't change any code. But that first time, that waiting, that's compilation. You're feeling compilation right there. So any questions on this before we get into recursion properly? Okay. And this was more background because you're starting to see this. Like, I just want to point out what that is. And this is a lecture where it kind of fit, like space-wise. I had a little bit of time, a few minutes here. But now let's get into the real meat of today is recursion. Recursion, we're going to introduce today, and then in 2 weeks with linked lists, we're going to hit you with a lot of recursion, and then when we get to trees, we're going to hit you with even more recursion. So this will keep coming up as we go throughout the semester. Today, I just want to do an introduction to get you used to the idea that recursion is something that exists, and it's super duper cool. I probably won't be able to convince you that second part today, not until trees, but we're at least going to introduce it today. So here's a recursive method, and a recursive method is a method that calls itself. That is the definition of a recursive method. There are, in other languages that aren't Java, there are also recursive functions, a function that calls itself. We're in Java, so everything's method. Bless you. But this is a method that calls itself, which seems weird. Like, how can a method call itself? So in this method, if I can hear you down here, you're being way too loud. So this is a method that calls itself. So we have this method that adds two integers, another really wonderful method. I know the methods are really boring at the first part of the semester. but it's going to add two integers. And this is one where we would want to write some unit tests for this one, because you have some smartass programmer who comes up with this monstrosity for adding two numbers. How are we going to tell if this one's right? Well, we're going to write some unit tests to make sure they actually did what they were supposed to do, have a nice thorough testing suite, because they didn't do just return A plus B like a normal person. They wrote this thing. Let's write unit tests to make sure they did what they're supposed to do. And let's, I think I changed it to add 3-4 instead of 4-3 in the memory diagram. But anyway, and this is a recursive method. Why is it a recursive method? We're defining a method named add. And in the definition of this method, it calls a method named add. This method is calling itself. These are the same exact method. It's not calling some separate method from somewhere else. It is calling itself. So this method call is a call of this method, which we're defining. We're calling a method while we're defining it. Before we even finish defining the method, we're calling it. This is wild. This is crazy. But this is what makes it a recursive method. It's a method that's calling itself. How does this work? And the best way to explain it, I could just give you the theory of what a recursive method is and how it works. Not going to do that. We're going to do it with a memory diagram. Yay. And this will be the first memory diagram in lecture where I'm using the tracing tool. So yeah, all right, let's do this. I did go back. I am going to use the tool, but I just want to point out, I went back to all of the previous slides for the semester. There were, I think, 5 memory diagrams that we did so far. And I updated those slides to have images like this of the completed memory diagram in the tracing tool. And I put an image like this both before and after the memory diagram in my slides. I kept the ones that we covered in lecture, the way we covered it in lecture, but I have the completed tracing tool memory diagram images in there as well, so we can see what those look like. And you know, I have my old style of doing this, but we're done with the slides. I'm not going to go through it in the slides. We're doing it this way, baby. So let me grab the code. Oh, yeah, no, I had it right, 4.3. I'm going to grab it from, I have a 3:12 lecture right before this. It's my first lecture of the day. My laptop decided to completely shut down a few minutes before lecture, so none of my stuff's open and ready the way I want it to be. So let's get IntelliJ up and running so I can grab the code. Oh, there's so many words. Here we 3, first recursion. Grab the whole thing. Go to the tracing tool and paste the code. Get rid of all this crap that we're not going to use. This is where I have to make sure I change it. 4.3. This. Everything bigger. Size. We don't need the heap at all today. Use up more room for the code. And okay. Again, this is the first time I'm using the tracing tool in lecture, so any logistical things, if anything's hard to see, let me know. Let's work together and get this working great. Because the rest of the memory diagrams, I want to use the tracing tool, so for obvious reasons, so it's consistent with what you're going to be doing in lab on your quizzes. Instead of using my slides, there's a big disconnect when I do slides differently than your quizzes, so let's get on the same page. And that's me getting off my ass and getting on the same page. So can I assume that compilation is a reason why Java is a strongly typed programming language? I don't have a good answer for you. So the compiler, I don't have a great answer for you, but I'll say this. The compiler can check our types. So the compiler does give us nice type checking. With an interpreted language, we wouldn't have type checking. It would still just be an error when the types mismatch, which you probably saw in Python before when you want to print out the number is, and then the number variable, but you forget to put str and then parentheses around it. It says can't concatenate a string with an int. You need to convert your int to a string first. You do get type errors in Python, but Python doesn't have the option of checking your types before it runs your program. It just has to crash when your types are wrong. So they are correlated, like the compiler can actually check our types and give us the ability to do a strongly typed language, but we could have a compiled language that's not strongly typed. That would be an option. But in practice, and maybe there's a deeper explanation that I just don't know off the top of my head, compiled languages tend to be strongly typed and interpreted languages tend to be not strongly typed in general. And I assume that's part of it, that the compilation can check that for us. Can recursive algorithms run into stack memory limitations for really big recursive algorithms? Yes. Yes, they can. Absolutely. And that's something I guess we won't see. I think I have it in my slides in the memory diagram there, but we won't see it doing the tracing tool. That if your recursive method is, I was going to say too recursive, but that doesn't make sense. If you put too many frames on the stack, you're going to run out of stack space. You're going to get that stack overflow error, and your program's going to crash. So whenever you're working with recursion, you do have to be aware of that you could run out of stack space. And for what we're doing in this course, the assignments and everything, it's just going to be built that you're not going to run out of stack space. But out there in the real world, you have to be aware that can happen. You can have too many calls on the stack when you're running recursion. In this course, whenever you see a stack overflow error, it's almost always, I say almost, but every time I've ever seen it from a student, it's because their recursion went infinite. And you, of course, can't fit infinite stack frames on the stack, so you'll overflow the stack. But it's possible to get that error outside of this class, even without going infinite. Forget to put a code block in a lab quiz, but you put all the info in a rectangular stack frame. Will you fail the quiz? Is this the first time this came up this semester? Oh, man. So let me give my disclaimer. Whenever there's a question of, will I fail for this, will I fail for that, will I fail for this? Short answer, I'm not actually going to answer this question. It's going to be handled on the grading side. Every case is usually pretty unique. It's going to depend on the exact mistakes that you made and the exact question being asked. If that question was all about, in this situation, if the question was all about handling a code block properly and you messed up your code block, it's probably going to be a fail. If it's a question about recursion and we just happen to have a code block as one kind of extra thing in there, and you put a code block instead of a stack frame instead of a code block, maybe you could still pass. It's going to be up to a lot of factors on that side of whether or not you pass on that one. I love recursion too. So whenever you have those specific questions, I'm not going to give specific answers. One, Paul's in charge of lab and oversees the quiz grading team. So what specific decisions they're going to make, obviously I have influence and say over that, and I do have the final say over all of you in my section, that if they go completely off the rails, I'm going to make some executive decisions for section B. Is this section? Whatever section this is. Section B. Yeah, because his are A, C, and E. Then I'll start overruling things. But as long as they're within reason, I'll stick with their decisions. So can't give, I'm going to hesitate, I shouldn't say I can't, but I'm going to hesitate to give firm answers on any quiz grading questions or interview grading questions. As a vague overgeneralization, if it's something that's not related to what's being assessed on that quiz at all, then I do not want to see you failing that quiz. So if it's a quiz about linked lists and you mess up I got to get a good example here. If it's a quiz, the first quiz is going to be about classes. The classes quiz is going to test your ability to create objects on the heap, handle your references, do pass by reference, assign by reference, and handle all that stuff. It's all about references, really, how references work in memory. And if during that one you make a mathematical error, or when you're printing to the screen, you put quotes around your string, even though there shouldn't be quotes around it. Like little things like that have nothing to do with references, classes, objects, constructors, any of that, then I don't want to see you fail. So if you do fail for something like that that's completely unrelated to what's being assessed, let me know and I can, we can take it from there. Messing up a code block, putting a stack frame instead of a code block, the more I think about it, the more I think that would just be a fail, though. That's a pretty big mistake. But it would be, I would leave that one up to the grading team. If they failed you for that, I would be like, yeah, that's a big mistake. If they passed you for that, I'd be like, okay, yeah, you got away with one. I would go either way on that one and just stick with what the grading team said. And we have to be a little lenient because of that question. It is pass-fail, so if you make one single mistake, it's not a fail. Like if you put, especially that example, you put quotes around your I.O. that's printed to the screen when it doesn't print with quotes, but it's a string, it should have quotes. No, it strips out the quotes. If that's your one mistake, you're not failing that quiz. In that case, come to me, I'll override that one all day, every day. If you forget to cross out your main stack frame, come to me. We'll talk about that. And I'll go yell at Paul and say, what the hell are you doing? If it's tiny little bullshit like that has nothing to do with your understanding, when I was updating my slides and making the memory diagrams, I forgot to cross out main a few times and had to regenerate the image, regenerate the trace, and then put the image back on the slide. It's easy to forget to cross out the main stack frame. So it's pass-fail, but you don't have to be absolutely 100% perfect. But you do have to be perfect on the stuff we're assessing. So on that first graded quiz, if you have the wrong number of objects, we have a list of things on this one specifically that'll be instant fails. Wrong number of objects on the heap, your references aren't referring to the right objects, you don't have the keyword this in your stack frames, you don't have your constructor calls. There are certain things related to exactly what we're assessing. Any mistakes there, you're done. You got to try again. But any tangential stuff not related to it, that's fine. Maybe you create a stack frame and you forget to name it, and it just says new stack frame on one of your stack frames, but you had it on the rest. Okay, you obviously just forgot to do it there, but you have completed the learning objective. You have that knowledge in your brain. You know what to do. All right, I'm going too long on this tangent. Let's do this memory diagram. Okay. So the first thing we're doing on any memory diagram, I'm just stalling because it's a new thing. It's easy enough, but it's new. I don't know how this is going to work in a lecture. All right, so the first thing we're going to do is create our main stack frame. I changed this to not even show the globals. We won't use globals at all this semester. If you ever put a variable in globals, you are wrong for the first quiz. I don't know if that would be a minor thing or something worth failing. I don't know. But avoid the discussion and just don't put anything in globals ever this semester. Yep. How'd you get rid of that? I was nervous using this because I would get this question. Yes, it is. I got to decide how much of a tangent I want to go on. It is something you can do. I didn't do anything magical that I need access for. What I did was create a browser extension that goes through the front end and just makes changes the way I want to get things set up the way I want. I do want to go on a little bit of a tangent like this, so let's do it. Plus, I get to stall a little more. I accidentally showed 312 solutions there. Whoops. Examples. I gotta make this bigger so y'all can see it. Just give me. Oh my God! I don't want to check for updates. Click the wrong thing. Oh, and there is an update available. Hold on, I just gotta update this quick. I can just do the editor actually. Okay, so what I did was I wrote, and I'll at least get this on the screen so you can look at the video if you're interested. You got to create a manifest.json that looks like this. You can, if you steal that. And then what I did was wrote some JavaScript that's going to modify the front end for me. And the one that you're talking about right here, I grabbed the global section and then deleted that element completely. So when I load the page, this code automatically runs as a browser extension, and then it removes the global section for me. And then the other things, making it fill up the whole screen and removing the menu. I didn't like how the menu took up so much space. I want every pixel that I can get when I have a limited amount of space. And I have to zoom in lecture. I need every pixel I can get. So I made those changes to this. I'll scroll in case somebody is using this. And I'll talk to Zaid. I told him that I'd get your feedback if somebody did mention it today. If you like this better than the default way, let me know, and this might just end up being the default way. So any feedback you have on this, let me know. Let Zaid know. Do the feedback thing on the button and say, I loved what Jesse did in lecture. And then Zaid will come to me and we'll talk about it. Okay, I stalled long enough. Where you have the main method, our program always starts with the main method. And the first thing we're doing here is creating a variable named result and calling this add method. Technically, what actually happens is the add method is called first. The method completely resolves, and then the variable is allocated on the stack. In our memory diagrams, we want to have our return arrow for the method pointing to where we're going to return it to. So we're going to create our variable first, our variable named result, and not give it a value yet, but we're going to create a stack frame with the name of the method being called and have this return to that variable. So whenever this method returns, we're going to put the value in that variable when it's returned. Add has A and B. A gets the value 4. B gets the value 3. And we're in, Zaid is one of the case, just for some background, in case, I don't think I've ever said this in lecture, in case you don't know. Zaid is one of the TAs for 116, and he built this tool, him and a few other students, mostly him though, built this thing from scratch. And it's still, what do I want to say? We're still getting the user experience down, and I've had plenty of feature requests for him. He's very good about getting them updated. If you have things that bug you about this thing, we can talk about it and get this thing working. Like, it's working pretty well, in my opinion, these days. I know some of y'all disagree, but you know what? It's better than pen and paper. That's what we used to do, and it sucked. But it's gotten a lot better. I think it's quite usable now. Usable enough that I'm finally using it in lecture, for what it's worth. That's kind of my bar of... It got good enough that I'm going to use it in lecture now. All right, so this stack frame, when we get into this method, this stack frame is going to execute this code and check. If b equals 0, b is 3. That is not 0, so this is false. We're going to go to the else if. If b is greater than 0, b is greater than 0, we're going to execute this line of code. And here's where we start to get into the magic. We're going to call the add method. And this method is going to, this stack frame is going to return whatever this stack frame returns. So we're going to get into another stack frame. And the trick with recursion, here's the big trick of doing your tracing diagrams of recursion. Just pretend it's not recursion. Don't do anything special. Don't overthink it. It's just a method call. We're calling a method. We're going to call the add method. Just like we did when it was called from the main stack frame, we're doing the same exact thing. We're going to call the add method. It gets A. A is going to have the value A plus 1 in the calling stack frame. So this is the stack frame that's making the recursive call. So this is the value of A we're using, 4. So A plus 1, A is going to be 5. We have B. And B is 3 in the calling stack frame. B minus 1, B is going to get the value 2. So we have a new stack frame for add. And the way this is set up, we probably wouldn't set it up like this on the quiz. The way we have this set up, there's no place for this method to return, so we're not going to do any return arrow. We used to have return arrows that would return to a stack frame in this case, but we're just not going to worry about it. You just don't have to have return arrows on these recursive methods. It'll be fine. We'll all survive. So this stack frame, no return arrow, but we're kind of implicitly saying it's going to return over here. Maybe we could return it to this variable. I'm not going to worry about it. If you lose points for that because Paul has a different answer, talk to me. We'll fix it. I'll fix that in grading. All right, so add is going to do the same thing. We just start over at the top of the method again. It's a stack frame for a method call. We start at the top of the method. We have the parameters, and we execute the code. If b equals 0, b, notice we have two values of b on the stack at this point in time. But remember, the stack frame on the top of the stack, or bottom visually, is always going to be the active stack frame. Since we're inside this stack frame and you can't access variables outside of the stack frame, we have no access to this b. And this is called, we always have this debate in TA meetings. This is called variable scoping. I don't think me or Paul use that word in lecture, so I'll try to start using it more. The fact that a variable is removed from the stack when a code block ends, and the fact that we can't access a variable in a different stack frame that's not the active stack frame, that falls under the umbrella of variable scoping, is like our key word of what to call that. So when the TA asks, what's variable scoping? You say, I don't know what that is, because we talked in the meetings. I'm like, TAs, they're not going to know the word scoping. So if they're still using that word, you just say, what the hell's scoping? And then they'll say, okay, when a code block and variables, when can I access it and stuff like that. All right, so this stack frame, b equals 0 is false. Elif, I'm thinking Python. Else if b greater than 0, that's true. So we're going to call add again. We're going to make another stack frame. Add. A plus 1 is 6. A 6. B minus 1, 2 minus 1, 1. No return arrow, so it's not returned to a variable. What we would do on a quiz, or what Paul should be doing, hopefully he is, I think he always does this, he's good about it. He's the one who got me doing it and is mad that I messed it up here. So he should be doing this on quizzes, is create a variable, create like int y equals add of a plus 1, b minus 1, and then return y. So there's a variable for that return value of the stack frame to go to. That's what I should have done here, but I didn't. All right, so this stack frame, again, we just start at the top of the method. If b equals 0, that's false. Else if b greater than 0, that's true. We're going to execute the same line of code. The method call, it's another stack frame, just like any other method call you've ever had in your life. In 115, I guess, not your whole life, in the past semester. So new stack frame, we're calling a method called add. A is going to be 6 plus 1. B is finally going to be 0. This is going to be part of my feedback that I want to get addressed. Like I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I have 14 pieces of information that I'm representing here, yet I have to have a scroll bar and scroll up and down. I want this condensed. I want to pack the information in there. So even when I zoom in, we can see the whole stack frame in one go. But if I zoom out, I think the text will be too small. Yeah, that's too small. Then we want to be able to read everything. All right, so this stack frame is going to execute. Add, we start at the top again, do the same thing. It's a stack frame for a method call. Start at the top, don't overthink it. If you pretend that this isn't even a recursive method, you'll be doing just fine on your memory diagrams. So we start at the top of the method again. If b equals 0, that is true. Return A. And this is where I should be doing the thing Paul would do. We're going to lose track of that return value the way I have this set up with no intermediate value, but we're going to live. We'll be fine. So this method is going to return A. This stack frame is going to return 7 back to this stack frame. So at this point in time, we have 4 stack frames of add all on the stack. And now that we have a better visual, what I was talking about before, the question was, can we run out of space here? if I tried to add 1,000,000 and 1,000,000 using this method, I'm going to have 1,000,000 stack frames, and I'm going to run out of space. The stack isn't going to be big enough to handle all of that, and we'll get the Stack Overflow error. So this method is quite limited in what it can do because it can't handle big things. Oh, Zaid's in chat. Yeah, so if you have feedback, you can tell him right now. I want to show this off, actually. I'll do it in a new stack frame. I'll show off Zaid's work. Create code block. And then I can cross it out. What? Oh, I'm so happy. The things that make me happy these days is crazy. All right, but I am so super excited to see that feature. We've been asking for that for a while. I think it just fell off the radar, so we got it back on Zaid's radar and got that done. All right, so this stack. So we have 4 add stack frames on the stack. Each one of these has its own copy of A and B. So a few things here. One, this is why we can share variable names across stack frames. Well, before I said this as, the math library has some method. What if it uses the variable x? We don't want to have to worry about that and say, well, since I called that method, I can't use the variable x anywhere in my code. We don't want that, but that's a little bit of a kind of weak selling point. But here's where we get a bigger selling point is we wouldn't be able to have recursion at all. It would not be able to exist if we couldn't reuse variable names in different stack frames. We would never, ever be able to have a recursive method because the parameters would all have the same name. It wouldn't be able to happen. So since stack frames are closed off, independent environments, we're allowed to have a stack frame with A and B, another stack frame with A and B, another stack frame with A and B, another stack frame with A and B. And each of these variables, A and B, are completely different variables in each stack frame. Each variable can have a different value. All these values of variables named A and B have different values. Every A has a different value. Every B has a different value. And that's perfectly fine. That's okay because they're completely separate variables, because they're in separate stack frames. This is completely allowed, and it enables recursion to happen. So when we get to this stack frame, we're returning A, which is 7, and we're just going to remember that this is returning 7. This wouldn't have to, if you got this code in your quiz, you wouldn't have to annotate this is returning 7. Maybe someday we'll add that, but it's not really needed. So we're going to cross this thing out. And this returns 7 to this stack frame. Since this one is crossed out, this stack frame is now on the top of the stack again, bottom visually, but top conceptually. This is now the active stack frame again because it's on the top of the stack. And this stack frame wakes up again. It was just sitting there waiting for its return value, but now that it's woken up again, it's the active stack frame, and it's got to continue its job. What it does is remembers where it was. It was waiting for this method call to resolve. Even though this was a method call of itself, of the same method, it doesn't actually care. It just treated it as a method call, just like any other method call ever. And that method call resolved to the value 7. And this stack frame is just going to pick up where it left off. Okay, this resolved to 7. What am I going to do? I'm going to run the rest of the code of this method, which is returning 7. So we got to the other side of the recursive call, a place we never thought we'd get because we called a method that wasn't full, we weren't even done defining yet. But it worked. It did return 7 just by tracing through the code. So this resolved to 7. This stack frame is going to return 7. Back to this stack frame where A is 5 and B is 2. That was waiting at the same point. It was waiting at this line right here. This resolved to 7. It's going to say, oh, hey, thanks for getting back to me with that. Gets the value 7 and says, okay, what am I going to do? I was waiting for this method call to return. It returned. It resolved to 7. I can resume what I was doing. What am I doing? Okay, I'm just returning 7. Then this stack frame returns 7. This stack frame says, oh, hey, my turn again. It was waiting for this to resolve. It resolved to 7. It's going to return 7, do the same thing as the other stack frames. This returns 7, all the way back to the main stack frame, which started the whole process, called add of 4 and 3. Gets the value 7, then prints it to the screen. When we get to the end of main, don't forget to cross out main, but again, if that's your only mistake is not crossing out main, I ain't going to be mad at you. And then the program ends. So we have a recursive call, but we just didn't overthink it. We just traced, one line at a time. And we never got in a situation where we're like, man, this is just some really crazy situation. What the hell do I even do? We just treated the recursive call as any other method call, and it served us well. We just got through it. Going back, I should go back to that conversation. It was talked about in chat too. I explained it. I can stop explaining things. Because that doesn't make sense if you're not watching chat. Somebody asked a question in chat, and I answered it right after they asked it without looking at chat. But then you don't get to ask questions and get answers. But we'll be fine. We'll live. It'll be okay. All right, so a few things. One thing I should mention, or maybe I shouldn't, let me just give a brief asterisk on this. I said this will overflow the stack if we add 1 million and 1 million. This is actually set up using tail recursion, so this wouldn't overflow the stack if you run this and try to add 1 million and 1 million. You know what? Let's go to IntelliJ and do it, since I'm done with the memory diagram. If we add 1 million and 1 million, because there's a small part of me that says it might break. I want a keyboard shortcut that will make everything bigger. That works well. There is actually one, but it bogs down my laptop and it's unusable. It takes like a minute to switch. So if I do 1 million, 1 million, test compilation. Oh, never mind, it did break. So this is a Stack Overflow error. I have that many stack frames that I just scrolled through, and we get the Stack Overflow error in main. Overflowed the stack. Why did that overflow the stack? It recognizes it as tail recursion, but I think there's something special I have to do to make it actually do tail recursion. I'm not going to worry about that right now. A little worried about it, but okay, so it does still break, but it shouldn't. I just got to do more. Control-Alt-Delete. Well, I like the spirit of that, but I'm on Mac, so it wouldn't even break anything. I'll still explain the difference anyway. Tail recursion is when the very last thing that a method does is return the result from the recursive call. Since all of these stack frames, all these intermediate stack frames, didn't have to do anything after this stack frame returned, you might as well have this stack frame return all the way to the main stack frame. And that's what tail recursion does. It says, well, if all these intermediate stack frames are done doing all their work, the only thing they have left to do is return whatever they get from the next stack frame. Let's just get rid of those stack frames entirely, reuse that space for the next stack frame, and not get our Stack Overflow errors. So it's much more space efficient and avoid Stack Overflow errors if you have tail recursion. This is tail recursive, but Java, maybe there's an annotation I'm supposed to set. I don't know. I haven't messed around with tail recursion in Java in a while, so I forget. Yeah. It just won't be tail recursive. They'll have to, like, if I do what I was mentioning, like the way we would do it on a quiz, we would have int y equals, then return y. Oh, it's not recognizing it as tail recursion. All right, I was not prepared for this discussion, apparently. I was expecting this symbol to change. This is the symbol for tail recursion. But I guess it's just the symbol for recursion with IntelliJ, or IntelliJ may be updated. I don't know. But I was expecting that symbol to change. Yeah, I'm just not ready for the tail recursion talk. We actually do plan on adding tail recursion way at the end of the semester, so we might properly talk about it. It's supposed to just be a fun tangent right now. You've been waiting a while. What's up? Java doesn't have global variables because everything, with the only exceptions are your packages and your imports, everything else has to be inside a class. So it's going to have class scope or object scope or stack frame scope. Nothing can be out in the global world in Java. It doesn't exist. So with this, each call of the function returns 7 to the previous because it was waiting, because it was just waiting not to compile, but to complete its process, to complete its execution. So like this stack frame, the only thing it's doing is waiting for the next stack frame to end, and then it's just going to return that. That makes this method tail recursive. But there's something I'm just missing where I got to tell Java, hey, this is tail recursive. Do the tail recursion thing. It's set up for tail recursion. It's just not doing the tail recursive thing. Yeah. The last statement has to be. But yeah, this is definitely not tail recursive. But when I had it as just return add. Like this should be, Like this should be tail recursive though. Like this is a tail recursive method. It's being confused by the I was thinking that, but even this, if I put this out here, I'm not going to mess with it more during lecture. I'll have to do that offline. I feel like there was one more point I wanted to make. I was going to think about running the debugger, but I don't want to. So any other questions? Or I want to, but I don't have time. So any other questions on this? But why don't we cross out the old A's and replace it with 7? So there's no variable assignment. If you look through this code, except this one, there's no variable assignment at all. And we only cross a variable value out if the variable's value is reassigned. That never happens in this code. Because we never say, like, A equals whatever, so the variable value is never crossed out. Come on, music, you should start. My laptop restarting is absolutely killing me.